Unit 6 of the Calculus Mechanics course. So that's going to be energy, that's going to be momentum, etc. We have kinetic energy for rotating body. Now, as you already know, you have kinetic energy when you have an object moving at some velocity in a linear fashion, okay? But when something is rotating in place and it is not changing its position at all, it can also have kinetic energy. It can have rotational kinetic energy. So let's try and derive the very hard equation for rotational kinetic energy. Okay, let's first start with translational kinetic energy. Translational kinetic energy is 1/2 mv squared. Rotational kinetic energy is 1/2, what's the analog of mass? Rotational inertia. What's the analog of velocity? Angular velocity. Oh, that was so hard. Okay. Rotating kinetic energy does not need to be accompanied by translational kinetic energy. So if I have a wheel spinning about its axis, and that wheel is not changing position in any way, it's just rotating in place, that is purely rotational kinetic energy. However, I can spin the wheel up, and I can spin it really fast, and I can give it rotational kinetic energy, and then I can throw it, in which case it will have both rotational kinetic energy and translational kinetic energy, which is a topic we're going to be covering later in the video. Okay, next up, we have the work energy theorem for rotating bodies, okay? Now, let's, bear with me here, bring up the work energy theorem for translational or linear changes, okay? It's initial position to final position of force as a function of x dotted with the displacement differential. Rewrite this in angular form, okay? Energy is energy no matter what. There is no angular form of energy, okay? But that is the integral from what's the position in terms of rotational analysis. That's going to be theta. Theta initial to theta final. What's force in angular analysis? That's torque as a function of x, or in this case, theta, dotted with d theta. Hey, that was really hard. I just needed to switch around the variables with their correct counterparts. So again, the work energy theorem has the exact same application it had before. If I want to impart rotational kinetic energy onto a body, I need to apply a torque through some distance theta. Next of all is probably one of the more complicated parts, and that's angular momentum. Angular momentum is represented by the quantity capital L. On your reference table, you'll notice that we have, like torque, two equations for angular momentum. The first of these equations is that your angular momentum L is equal to your radius vector crossed with your linear momentum P vector. The second equation of which states that it is also equal to your moment of inertia times omega, okay? Where this is the analog of mass times velocity, which we are so familiar with. I think the best way that we can start to understand angular momentum is as we work through two different problems, okay? The first problem I'm going to go over with you guys really shows and demonstrates this equation. The second problem is going to really demonstrate this equation. So first, let's start off with a very, very common type of angular momentum problem on the mechanics exams. Usually shows up more than once actually, is if I have a disk and that disk is spinning around a central rod as such, that is a disk spinning around a central rod. Let me try and draw that better so that we can have a better understanding of what's going on here. Disk spinning around central rod, okay? And on top of that disk, separated some distance from that disk, is a second disk. We have a central rod, one disk spinning closer to the top, one disk spinning closer to the bottom, both of which are separated, okay? We are given that the moment of inertia of the top is equal to the moment of inertia of the bottom, which is equal to, let's say, 12. I don't know. So then we would be given that the velocity, or the angular velocity, of the bottom disk is in the negative direction, let's say -2 radians per second, and the angular velocity of the top disk would be +6 radians per second. You know what, for the sake of demonstrating complexity, I'm going to say the top one is 12 and the moment of inertia of the bottom one is 10. Okay? So where do we define positive direction? Positive direction is counterclockwise in this direction. So therefore, the bottom disk having a negative angular velocity would be spinning clockwise, and the top disk having a positive angular velocity would be spinning counterclockwise. Okay, so here's your problem. Once the disks are set up like this, spinning at their given speeds, the top disk is released and falls onto the bottom disk. Find the final velocity, angular velocity, of the two-disk system. So this is a conservation of angular momentum problem. Let's calculate our total angular momentum. First, we calculate the angular momentum of the top guy. Angular momentum of the top, let me make sure you guys can see this. Angular momentum of the top is our moment of inertia 12 times our angular velocity 6. Angular momentum of the bottom is our moment of inertia 10 times our angular velocity -2, which is equal to 72, this of which is equal to -20. Therefore, the total is going to be 52. This value, conservation of angular momentum, still exists, okay? Momentum is always conserved. So our total initial angular momentum has to equal our total final angular momentum, all right? So therefore, we're going to write that 52 is equal to the net moment of inertia times the net final velocity. So from the previous unit, you will know that since both of these disks are spinning around the same axis, the net moment of inertia is just the sum total of the component ones. 52 is equal to 12 plus 10, 22, times our final angular velocity. Okay? So we do 52 divided by 22 to give us our final angular velocity, which would be 2.36 radians per second. Am I rounding right? Yeah, 2.36 radians per second. So this is probably the more simple of the two problems, okay? Now let's look at this example, okay? This equation would be used when you are given a problem set up like this. Okay, so this problem is going to sort of unite everything we've been talking about so far. So here is the problem. You have a ball, a 1 kilogram ball, moving at 5 meters per second in the rightward direction. Okay, and you have a rod with mass 4 kilograms, length 1 meter, and moment of inertia of 4/3, and that rod is connected to an axis of rotation at the end of the rod, up top here. You are given that it is a rod of uniform density, meaning that the center of mass of the rod is directly in the center, and you are given that the rod is stationary, meaning that this small ball will collide with the rod right at the bottom, and as a result of that collision, the ball will swing upwards some amount. Your job here is to determine the final height h that the ball reaches. Final height h of the ball at the top of its swing. Okay? So, first thing we got to do is we got to employ conservation of momentum. Okay? The momentum of the ball is going to be mass times velocity equals 1 times 5 equals 5. Okay? But we want angular momentum. We want to observe conservation of angular momentum because we're observing a rotating system. Okay? So what are we going to use for our radius in this case? We calculated the linear momentum. How do we find radius? Well, you'll notice that the radius, the distance from our center of rotation to the ball, is constantly changing as the ball approaches. However, we are only concerned with the radius at the instant of collision, in which case the radius would be the length of the rod, or 1 meter. The angular momentum of the ball is equal to the linear momentum crossed with the length, 1 meter. Okay? Now, they intersect at exactly 90 degrees, meaning that our sine theta is going to be 1. So therefore, the linear momentum, or excuse me, the angular momentum of the ball is going to be 5. Since the rod is stationary at the beginning, it is not moving, it has no angular momentum. Therefore, our total angular momentum for the system is going to be 5. Okay? You are also given that upon collision, the two things stick together. Okay, so that tells us it's a perfectly inelastic collision, which means the final velocity of our ball and the final linear velocity or angular velocity of our rod will be the same. Okay, so our total angular momentum, 5, is going to equal the angular momentum of this system now. Okay, is going to equal the total moment of inertia of the system multiplied by the final angular velocity of the system. Okay, so we know that the moment of inertia is, for our rod, is 4/3, and the moment of inertia for any single point mass is equal to that mass times its radius squared, as given on your reference table. Okay, so therefore our net moment of inertia, the total moment of inertia from the system, is going to be 4/3 the moment of inertia of the rod plus the mass of the ball, 1, times its radius squared, which is going to be 1. Yes, 1, which is going to equal 7/3. So our angular momentum of the system, 5, is going to equal 7/3 times the final angular velocity. Divide both sides by 7/3, and we get our final angular velocity is going to be 2.14 radians per second. Okay, now that we have this, we need to switch gears and start tackling this problem from a conservation of energy perspective, because now we have a velocity and we're trying to find the final height. Okay, so from here we can calculate the rotational kinetic energy of our system is 1/2 the moment of inertia times omega squared, which is going to be 1/2 times, where is it, 7/3, times 2.14 squared, which is therefore going to be 5.34 joules. Okay, so since that's our kinetic energy, once the rod reaches the top of its motion, all of its kinetic energy will be expended, and that will equal the gravitational potential energy of our system. Okay, so gravitational potential energy is, as we know, near Earth's surface, going to equal mgh. But the actual h, the actual height that we traverse, is the height traversed by the center of mass. Okay, now don't get fooled. We said before that this is a rod of uniform density, and therefore the center of mass of the rod is going to be right in the center. However, we now have another mass added to our system, so our center of mass has changed. So let's consult the equation for center of mass for finite systems. Let's consider that the bottom of the rod is going to be our 0 coordinate, okay? Therefore, the center of mass contribution from the ball right here is going to be 0 in the numerator. However, if I were to bring this equation down here and continue analyzing, I would then plug in the contribution from the rod, which would be the mass of the rod 4 times its distance from our reference point, which would be 1/2 the length, which would be 1/2. Okay? So now this is our total contributions in the numerator, and now we need to calculate total contributions in the denominator, which is going to be the mass of the rod plus the mass of the ball to get the mass of the whole system, 5, which therefore simplifies to 2/5. So the center of mass of the system is going to be 2/5 of a meter above our reference point, 0. Okay? So now we know the initial height of our system. The initial height of our system is 2.5 meters. Okay? And remember, the change in gravitational potential energy equals mg times the change in height. So therefore, our change in height is going to be h final minus h initial. So our change in gravitational potential energy is going to be this 5.34, our kinetic energy, equals the total mass of the system, which is 5 kilograms, times the gravitational constant g, times our hf minus 2/5. Okay? G, of course, we're going to assume is 10. So I'm going to divide 5.34 by 50. And now I'm going to add 2/5 to both sides, such that my final height, h sub f, is going to be 0.5 meters. Whereas the initial height was 2/5 of a meter, or 0.4 meters. Okay, but we're not done yet. We know that our change in position, delta x, is going to be our final position minus our initial position. So it's going to be this number minus 2/5, which is, I'm doing it in my calculator because there's other decimal places in my calculator that I rounded off that I want to get back now. Okay, so the precise delta x is going to be 0.107 meters. Okay, and as we know, delta x is equal to theta times r, the radius of rotation. Our radius of rotation was the distance from our axis of rotation to our center of mass. So our radius is different here. It would have been, where did I calculate radius of rotation? Our radius of rotation was 1 minus our initial height, so our radius of rotation is 3/5. Okay, so delta x equals theta times 3/5. So we multiply this by 5/3, such that our theta, the angle theta traversed, is going to be 0.18 radians. 0.18 radians. Now I know the theta that I've traversed through. Now I can calculate the final height that the ball reaches. Okay. So the change in x for my ball is going to be the final height of my ball minus the initial height of my ball, okay, which is also going to equal the angle theta the ball was traversed through times its radius of rotation r, and in this case the radius of rotation r is 1. That equals theta equals 0.18. Therefore, the final height that my ball reaches is going to be 0.18 meters high. Okay? Now, you guys might look at this problem and say, that's super hard. They would never give us a problem like that. No, you're wrong. This is probably the closest approximation in difficulty you have to the full-length FRQs you'll be seeing on your exam. And there are 4 FRQs on your exam. And this is, I don't want to say that this is a subpart, I want to say that this is closer to the difficulty of a full length of one of those 4 FRQs. Okay? So anyway, that's our final answer. The first part of the FRQ might have been to calculate the final angular velocity here. Okay? Anyway, let's move on. The final part of this unit is going to be its application in orbital mechanics. Okay? Orbital mechanics is pretty much the study of satellites moving around the Earth. Okay? Now, here in the physics class, when we use the word satellite, we don't mean a flying GPS computer that connects to your phone. A satellite is used to describe any object in orbit. Okay? Note that that's what we mean when we say satellite. Therefore, by definition, the moon is a satellite. When we are analyzing the motion of satellites around the Earth, okay, we are going to have, let's say, some object, And if that object were stationary, the Earth would just pull it in with the gravitational field and the two would collide, okay? Therefore, in orbital mechanics, we assume that there is some velocity of the object as it orbits around the Earth. The object is going to have some kinetic energy, and the object is going to have some gravitational potential energy, okay? Now, recall before that gravitational potential energy, the equation for which is negative g m1 m2 over r, okay? At any distance greater than 0 and less than infinity, which is pretty much any distance, at any distance away from Earth, your gravitational potential energy will be negative, okay? Therefore, it's important to understand that the closer you get to Earth, the more negative it becomes, and the further you get from Earth, the less negative it becomes. Such that as you get further and further and further away from Earth, your gravitational potential energy approaches 0, and as you get closer and closer and closer to Earth, your gravitational potential energy approaches negative infinity. That's what this negative is doing for us. So, again, recall that kinetic energy is going to equal 1/2 mv squared. Or if you're dealing with this in rotational dimensions, 1/2 I omega squared. Okay? So since we are dealing with an orbit, we are dealing with an object in circular motion around a host, we are going to have a centripetal force acting on that object in order to keep it in orbit. And the centripetal force is equal to the mass of the object times the centripetal acceleration. And we know from the equation on the table that the centripetal acceleration is equal to v squared over r, or is equal to r omega squared. We would be able to say that if we want to interpret this in linear variables, that our centripetal force is equal to mv squared over r. Okay? Now, what is the centripetal force in this case? What is the force that is constantly pulling on the object in order to continually keep its velocity vector turning? Okay? What is that force? In this case, it's going to be the gravitational force. Okay? So therefore, I'm going to say that my gravitational force equals mv squared over r. Okay? And that's going to be rewritten as g m1 m2 over r squared. Okay? Now, to avoid confusion from here on out, I'm going to say that big M is going to be the mass of our host, and little m is going to be the mass of our satellite. So let me rewrite this equation with that new definition. Okay, and of course, this stays as the mass of our satellite. Therefore, in this equation, these two cancel out. And these cancel out. Therefore, we can rewrite this as the velocity squared of our satellite in its orbit around Earth is equal to g times the mass of Earth divided by the radius that it orbits at. Or we can take the square root of both sides and write it as such. Okay? Important equation to be derived. We can also approach this in saying that the total energy in our system is equal to the potential energy of our system plus the kinetic energy of our system, which is therefore equal to the gravitational potential energy, negative g, big M, little m over r, plus 1/2 little mv squared. Okay? Now, if we reconsider this derivation that we were doing right here, we can rewrite our variables in to get back to our original setup, that the centripetal force is the gravitational force, okay? If I, again, remove my r from both sides, I get that mv squared equals gm little m over r, okay? Gm little m over r. I have the negative of that right here. Therefore, I can write that negative mv squared plus 1/2 mv squared is equal to the total energy of the system. So, negative mv squared plus 1/2 mv squared equals negative 1/2 mv squared. The total energy in my system is negative ke. Okay? And that also means that if the total energy in my system is equal to negative KE, and that equals the gravitational potential energy plus the kinetic energy, then if I subtract kinetic energy from both sides, I'd get that negative 2 KE equals U sub G. That my gravitational potential energy is always the negative of twice my kinetic energy. All right, and one more characteristic that we need to understand here in orbital mechanics is a concept known as escape velocity. Okay, so let's particularly define what escape velocity is. Escape velocity is the total amount of energy necessary to completely escape the gravitational force, to completely escape the gravitational pull of a planet. Okay? So in our equation for gravitational potential energy, we can see that in order to completely escape the gravitational pull of a planet, we must completely reduce all of the negative part of our gravitational potential energy. Okay? Therefore, in order to completely drive our gravitational potential energy to zero, we must travel an infinite distance away from the planet. Okay? So, well, that sounds like some pretty hard math. Well, it's not really. In order to travel an infinite distance away from the planet, you're pretty much saying, I want to make my gravitational potential energy zero. Okay? So, if we want to do that, we need to calculate our initial gravitational potential energy. Let's say we're calculating the escape velocity of Earth from the surface of Earth. Okay? And again, the radius component, r here, is calculated from the center of mass. So let's say we plug in the radius of Earth, we plug in all of our mass of Earth, mass of our objects, all of this, and we say that our gravitational potential energy is negative 40 megajoules. Okay? Which on your reference table you would be able to convert to negative 40 times 10 to the 6th joules. Okay? So this is how much energy I am in a deficit of. So I need to put in 40 times 10 to the 6 joules in order to completely escape the gravitational pull of Earth. Okay? So, in order to completely escape the gravitational pull of Earth, I would be launched up into the air with some initial velocity. Okay? And that initial velocity must be such that I have a kinetic energy equal to or greater than this number. So I'm going to set that equal to my initial kinetic energy that I need to have in order to escape Earth. Okay? Equals 1/2 mv squared. All right? Now let's bring that derivation over here where I still have some space. And I'm going to say that my initial kinetic energy, 1/2 mv squared, must equal my initial deficit of gravitational potential energy. G m1 m2 over r. Okay? So we're going to rewrite this with little m representing the mass of our object, big M representing the mass of our planet. Therefore, these two m's cancel. I'm left with the 1/2 v squared equals g big M over r. V squared equals 2 g big M over r. And therefore, my escape velocity, the initial velocity I would need to escape the gravitational pull of Earth, is equal to rad 2 gm over r. Okay, there we go, guys.